तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Good morning. Today we are going to take that final step where we are going to talk about how the Poynting vector allows radiation on the one hand, what we are talking about as our one dimensional wave equation, and circuits on the other hand, how they talk to each other. I will only touch this topic because it is not properly part of this course at all. This course is supposed to stop short of antennas. However, you cannot understand the rest of electromagnetism till you know where antennas are supposed to fit in. So, last time we had written down the Poynting theorem. The Poynting theorem said the surface integral of E cross H dot ds over a surface is equal to negative of volume integral over the surface of magnetic energy, the flux of magnetic energy, the rate at which magnetic energy is increasing with the minus sign, so rate at which magnetic energy is decreasing. Similarly, rate at which electric energy is decreasing, and the rate at which energy is getting dissipated. And as I told you, if you look at this piece, this is basically what we call our inductor L, and this is what we call our capacitor, and this piece is both resistors and voltage sources. So, the entire right hand side of this equation is circuit theory. And what this equation is saying is, when circuit theory fails, the failure is represented by this surface integral of a quantity E cross H dot ds. So, as long as this conservation theorem holds, you are basically satisfying KVL and KCL. Why do I say that? You are satisfying KVL and KCL because it is this term, the E cross H, that includes terms that break down E equals minus grad phi except in capacitors, and V is equal to L di dt except inside inductors. Okay. So, inside an inductor you have this, and inside a capacitor you use stored energy, but outside these components, if you look at what is happening inside a circuit, what we are saying is that you can do a addition of voltages and this holds, that is loop integral E dot dl is equal to 0. That is what this is saying, and that is what this is saying as well. The place where this fails is inside an inductor, but we explicitly take inductors into account. We do that because inductors are really low frequency elements, so we can take care of them without invoking waves. So, magnetic stored energy, electric stored energy and dissipation and batteries is already part of our theory of circuits. Now, we want to add one more piece. Now, to prove that we need to add this piece, I am going to talk about a particular problem. We have already done the case, we found one solution to this wave equation. Let me remind you, the wave equation I solved was del squared Ex del z squared minus mu epsilon del squared Ex del t squared was equal to 0. We solved this equation and we found that Ex is equal to some function of z minus Ct plus another function of z plus Ct. And as I discussed with you, these f and g can be any function. So, I have used things like triangles and rectangles just to make that point. But in electrical engineering, we have some favorite functions, the function that is easy to understand and manipulate. And so, we usually talk about sines and cosines. So, we say that E is some A sine z minus Ct plus, in fact, I will give an angle also, plus delta plus B sine z plus Ct plus delta prime as my function for Ex. Since these can be arbitrary functions, they can also be these functions. There is nothing in there that says they can't be. Only thing that is important is they should be functions of z minus Ct, which tells us that they can actually be some z minus Ct times something. I am going to call it k plus delta, and z plus Ct times k plus delta prime. As long as their functions are z minus Ct and z plus Ct, they fit this form. If you write this out, what you get is A sine kz minus kct plus delta plus B sine kz plus kct plus delta prime. So, it is some function of z, some function of t through these things. Now, if we go back to this equation and substitute that, what we get? The second derivative of sine of anything gives me minus sine of the same thing. So, I will get minus k squared times the entire function Ex minus mu epsilon. If I take the time derivative, I will get minus kc squared here and plus kc squared here, which are both kc squared, times Ex equals 0, which tells me, because the k squared cancels out, that mu epsilon c squared is equal to 1, or c equals 1 over square root of mu epsilon, as we worked out earlier. So, this satisfies this equation. Now, I am going to think of a particular problem. The particular problem I am going to think of is that I have a slab of copper, and that this is the z direction, this is the x direction, this is the y direction. So, I have this solution for the electric field arriving at the copper plate. The electric field is this way, magnetic field is this way, and E cross H is in the z direction. Now, of course, you know that the magnetic field is along plus y for this problem, because when you want to solve for the magnetic field, you use Faraday's law. So, we will say curl of E is equal to mu the minus sign del H del T. We are working in the y direction. E is along x, derivatives along z. So, it is y hat del E x del z is equal to minus mu del H del T. So, if you take del E x del z, that will take the sign and make it a cosine. So, you get that minus mu del H y del T is equal to cosine of, there is a derivative. So, k times the cosine of k z minus k c t plus delta. If I now take the time integral of both sides, that should give me h y. So, that will tell me that h y is equal to minus k over mu times the integral of this with respect to t, 1 over minus k c times sine of k z minus k c t plus delta, which is the same function as for E x. We know that h y and E x look the same. The k cancels out, the minus sign cancels out. So, h points along the plus y direction. But if we look at this case, we will be dividing by plus k c, and so there is a minus sign left over and h will point the other way, in which case E cross h will point in the reverse x z direction. So, this is the forward wave, this is the reverse wave. So, for now let us not worry about the reverse wave, we will only worry about the forward wave. So, I have a wave that is a sine k z minus k c t. I can always absorb delta into t. I shift my time and delta can be made 0. So, that is my wave. E x is equal to a sine k z minus k c t. This is vacuum, so it is epsilon naught mu naught. So, c is equal to 3 into 10 to the 8 meters per second square per second. Let us assume here this copper is also epsilon naught mu naught, but copper is a conductor. So, it has a sigma. Now, this wave is going to come and land on this copper plate. What happens? Well, at the end of last lecture, I had worked out most of the boundary conditions, the matching conditions across an interface. I had worked out that just as in statics, because divergence D is equal to rho and divergence B is equal to 0, D normal and B normal are continuous with only condition being D normal. This is how we indicate the jump in D, which is dn2 minus dn1. So, we want to say dn2 is equal to dn1, but there is only one condition, which is the jump in D normal is equal to the amount of surface charge. If you happen to have a system where there is surface charge present, then when you do your Gaussian surface, you always include that surface charge as well. So, the D normal will not be continuous, it will jump according to the amount of surface charge you have. That comes straight from this equation. When we did the Faraday's law, we immediately saw E tangential is continuous. And when you look at Amperes law, you have a slight difficulty. You have the material, you draw a Stokes curve, you make sure that the height h is much smaller than the length L, and we do a integration in some sense. So, I have chosen the direction in which I will do integral h dot dl. Integral h dot dl on this curve is hardly, these two vertical lines hardly contribute anything because h is much smaller than L. So, it is equal to h tangential 1 minus h tangential 2 times capital L, because it is h dot dl over this section and then minus h dot dl because the direction of the integration changed on this level. So, you get h tangential 1 minus h tangential 2 times L, but it is equal to surface integral curl of h dot ds, which is equal to surface integral j dot ds plus surface integral del d del t dot ds. The same argument that allowed us to throw del b del t, namely the area is L times h. Since h is very small, area will be very small, so this term goes away. However, if you have a surface current on the surface, that surface current does not go away, because ultimately what we are saying is loop integral h dot dl is equal to current enclosed, and if the current is basically on the surface, then you will have some amount of current captured. So, you end up with a condition that says h tangential 2 minus h tangential 1 is equal to current, surface current at that point. Now, let us go back here and look at what this is saying. If we assume this conductor has an infinite conductivity, then there is a surface current, and this surface current will be connected to h y. So, when the wave reaches the wall, there will be an electric field pointing up, there will be a h y pointing this way. Whatever current is on the surface must match h y, because h y on the other side is 0. So, if I draw a Stokes line, Stokes curve, there is h this way, there is no h this way. So, my entire loop integral h dot dl is equal to h y times L, where L is this length. What is the enclosed current? Well, the enclosed current, let us say it is in the vertical direction, is equal to j surface in the vertical direction, which will be j surface j x into the length L. So, h y is equal to j x. Now, this is a very good conductor, which means the electric field must go to 0. If the electric field does not go to 0, electric field is continuous. So, I will have an electric field inside the metal, and I already know that electric field inside the metal means J is equal to sigma E. If sigma is infinity and J I already know is some finite value given by Hy, therefore E must be 0. You can't have any electric field inside the metal, but I have electric field in the wave. So how do I solve this problem? The way electromagnetics solves this problem is simple. It knows that Hy is okay, but Ex should go away. So what it does is that at the wall it has the wave Ex Hy, and it also adds a reflected wave. Now remember that if we have plus sign here, what that will do is your Ex has a Hy pointing the other way. But there is no real reason why I should take Ex with Hy pointing the other way. I can take Ex pointing downwards and Hy pointing the same direction. Both ways E cross H is pointing backwards. Let me repeat that. If I have the electric field pointing up, Ex, magnetic field pointing sideways, Hy, X cross Y is Z, so I get E cross H in the positive Z direction. Wave is moving forward. If I have Ex but Hy pointing the opposite direction, that is minus Hy, then E cross H is in the negative direction. If I have E pointing downwards and H pointing in the negative Y direction, then in fact I have E cross H again pointing forward. But if E is pointing downwards and H is pointing along plus Y, then it is backwards. So it depends on not just the direction of E, but the direction of E relative to the direction of H, because E cross H has to do with the cross product. You have to take your right hand rule and apply it and see in which direction you will tighten a right handed screwdriver to make it go in the direction of E cross H. So the direction that I want is this direction. Now what happens? At the wall, the plus Ex and the minus Ex cancel. I will end up with Ex 0, which is continuous. And because it is continuous, inside the metal there is no electric field. But the Hy's add up. I get twice the Hy, which supports a current. So inside the material, I am going to have Jx, but I am not going to have any electric field, and my J dot E will be 0. Now let us look at that. Where did the energy go? I have my Poynting theorem. My Poynting theorem said surface integral E cross H dot ds over a surface is equal to volume integral of basically E dot del d del t plus b dot H dot del b del t plus J dot E dV. These two terms are essentially steady state. If I average over one time period, nothing is happening. J dot E is 0, perfect conductor. So this right hand side is 0, which means the left hand side also has to be 0. How can that be? Well, if you look at it, the surface we are talking about is a cylinder that is piercing this slab. E cross H is in the z direction. So E cross H dot ds does not contribute to the sloping sides. Electric field is 0 inside the wall, so there is no E cross H. So all the E cross H is here. So this is surface integral over the surface 1 is just this piece of E cross H, and I am saying that should be 0. Well, it is 0 because there are two waves. There is a wave which I will call E cross H forward plus an E cross H backward. Dot ds. There is this piece and this piece. I know that one of these is pointed in plus z direction, the other is pointed in the minus z direction. Therefore, when I dot product these two with ds and ds points in the z direction, I am going to get the amount of power injected by the forward wave minus the amount of power taken away by the backward wave. But in order to make electric field 0 inside the wall, I had the reflected wave and the incident wave, these two waves equal in power. Otherwise, this Ex would not have cancelled this Ex and I would have had some electric field inside the copper. So, it means these two E cross H's must be equal and they have opposite sign. So, that is why this also becomes 0. So, this is a case where I have an electric field entering and I have an a wave entering and a wave leaving, and if this wave brought in 1 watt of power, this wave took out 1 watt of power, and so there is no net transfer of energy from the wave to my material. Now, let me take a case where sigma is not infinity. Supposing sigma is some reasonable number, not very large, not very small. What happens? This is still true. Poynting theorem is a general theorem that we derived without making any approximations. So, the entire theory must still hold. What happens is that at this interface, the incident electric field Ex Hy, they go into the material, and because J is now not, that is sigma is not infinity and J can be requires an electric field to exist. Now, in fact, when Hy is present inside the material, you need an Ex to be present as well. What happens is the electric field goes into the material, magnetic field goes into the material, and at that point the presence of the magnetic field implies a current Jx, and this Jx implies an Ex because J is equal to sigma E. But Jx times sigma Ex is a dissipation, it is heat, this is Ohm's law, and therefore, the energy in the wave starts reducing. The J reduces, and therefore, the amplitude of the electric field and the magnetic field reduce. There is a smaller J as a result, the amplitude of the electric field and the magnetic field further reduce, and you have an exponential decay of the electric field and the magnetic field. This effect, whereby a wave enters a material and dissipates its energy, comes under different names. One name in which you see it is eddy currents. Another name in which you see it is skin effect. This is the common name that we usually give, the skin effect. And from our point today, the important thing to understand is this represents heat loss a wave impinged on this plate and heated it up, because J dot E means energy has gone into the material and the plate is getting hot, which means that there is power being transferred by this wave to the material. So, it means that this solution that we have not only exists, but it is capable of carrying energy with it. So, now we have several characteristics to this thing. Let me enumerate them so that you can see where we are going. Decays as 1 over r, travels with speed c equals 3 into 10 to the 8 meters per second, carries energy with it. Now, if you look at this table of observations, you can see that these are all the things that light satisfies. If you look at the sun and you look at light going out from the sun, we know that the total intensity of the light, which would correspond to E cross H, okay, is proportional to 1 over r squared. In our case also, E cross H is proportional to 1 over r squared. Light, of course, travels with the speed of light, and light carries energy with it. Otherwise, the sun's light could not be giving energy to earth, could not be heating it up, could not be giving energy to plants and giving us photosynthesis. So, we have almost confirmed that this kind of solution corresponds to what we see in optics. But there is still one basic question left. The basic question is, under what conditions can I say I have circuit theory, and under what conditions do I have to add this extra effect of radiation? We know now that if a wave hits a plate, the plate will heat up. So, this is now confirmation that this kind of solution can actually interact with the material and can deliver power to it. But that is a different statement from how to generate it and how to make use of it. For example, how does a shortwave radio work? How does a broadcast station send out radiation? And what makes a circuit describable by standard KVL and KCL, and when does a circuit require a better treatment than that? It is a very important question, because it tells us the limits of circuit theory, tells us when we have to be careful and when we can just forget about all this stuff and go back to voltages, currents, inductors, capacitors and resistors. Now, to answer that question, you have to go back to this problem of a wave that strikes a plate, and you ask something slightly different. Supposing I have a wave and it strikes a plate, it is a thin plate, and at the top of this plate I connected a resistor to ground. So, this plate, if you like, is just hanging. Now, what I want to know is there some combination of circumstances by which I will get a current? For example, if this were actually a light bulb, can I make this light bulb glow? So, that would be a kind of a situation where I have electromagnetic radiation come, hit this plate, the plate gives power to this bulb which again creates electromagnetic radiation. But we are not thinking in terms of that. I would like to know if I can obtain this radiation and make use of it. Instead of putting a light bulb, I could more usefully put an amplifier and connect it to my speakers. And then I could get my broadcast and listen to it in my home. So, the question is, what kind of phenomenon will allow a current to flow in an outside circuit? Now, the first thing to understand is that phenomenon is not what I described earlier, because if you take the electric field E x and you take this magnetic field H y, and this H y causes a current J x, and this J x dot E x dissipates the wave decays naturally. The problem is, whatever energy was there in the wave got dissipated in the plate got hot. But if a plate gets hot, it does not give me a current, it does not give me something I can amplify and listen in a speaker. Rather, I want to get this wave energy, and instead of dissipating it inside this plate, I want it to come into the outside circuit. So, the question is, under what conditions is that possible? Well, to answer that, we have to go a little deeper into how I wrote down those equations. In fact, I did not write down any equations, I just drew pictures. So, I am going to look into this phenomenon we are calling absorption of radiation by materials, or skin effect. So, I have this wave has somehow entered a material region. So, it is inside a region with permeability mu, permittivity epsilon, and conductivity sigma. And at z equals 0, the electric field is E x or E naught in the x direction, say sin k z minus k c t plus delta, and I am removing the delta because I can always adjust time and make delta 0. Now, to analyze this problem, I have to write down wave equation inside the material. So, let us look at that. I start with Faraday's law. And del B del T is minus mu del H del T. Then I go to Amperes law. Curl of H is equal to the current plus epsilon del E del T, that is del D del T. And again I will combine these two equations. I can see that in order to eliminate H, I must take the curl. So, I get curl of E is equal to minus mu del del T of curl of H, but curl of H is this. So, it is equal to minus mu del J del T minus mu epsilon del square E del T square. It is the same derivation I have done earlier, except I have one additional term, because the earlier wave equation I derived had no currents and no charges. Now, when you do this problem exactly, large number of complications, so we are going to make certain assumptions. The assumption we are going to make, which is most important perhaps, is that the divergence of J, which is minus del rho del t, is small. The idea is that in that case I can say divergence of E, which is 1 over epsilon divergence of D, which is therefore rho over epsilon, is 0. How does that help us? Well, when you look at the left hand side, you can go back in your notes and see how we derived it. You will find curl of E is actually equal to gradient of divergence of E minus del squared E. This term would be present if you have charge density, but I am going to choose to drop it. There are situations where you have to keep it, but for understanding skin effect you do not need to keep it. In fact, for most effects you can safely drop this term. So, then that gives me my new wave equation. It does not have the charge density effect, but it does have current, but I am saying the current has a very small divergence. So, I get minus del squared E is equal to minus mu del j del t minus mu epsilon del squared E del t square. So, one new term. I am going to specialize to one dimension, and I am going to use the fact that my electric field has a very specific form, and incidentally I am going to call this K c as omega. It is just notation, we will understand what K and omega are in a little while. So, what do I get? If I substitute one dimension, then I will get minus del squared E x del z squared is equal to minus mu del j x del t minus mu epsilon del squared E x del t squared. Substituting from E x equals E naught sin k z minus omega t, you can substitute it in. What do you get? You get k squared E x, because if I take the derivative of sin k x k z, it will become k cos k z minus omega t. I take the derivative again, I get k squared with a minus sign sin k z minus omega t. So, I get minus k squared, and there is already a minus sign, so it is plus k squared is equal to minus mu del j x del t plus mu epsilon omega squared E x. But we have a new term here, J x, and here I am going to use the presence of conductivity. If conductivity is present, then I know this implies J x is equal to sigma E x. So, I substitute that in here. I can replace J x by sigma E x. So, mu sigma del E x del t. Now, here you will see a problem, because when I substitute del E x del t, I will get a cosine. My sine will become a cosine. So, I will actually end up with k squared sine kz minus omega t is equal to minus mu sigma omega cos kz minus omega t plus mu epsilon omega squared sin kz minus omega t, which is very difficult really to make sense of. So, this is why when we do these problems, instead of using sines and cosines, we tend to use complex exponentials. You have already been introduced, I am sure, to phasors, and the purpose of using phasors is simply that the 90-degree shift is very easy to handle. When we take a derivative of a cosine, you get a sine, and then you are stuck with a lot of algebra. But instead, we will use cos of kz minus omega t is equal to real part of e to the j kz minus omega t. And then we will work with these phasors. So, in terms of phasors, Ex is equal to sum E naught e to the j kz minus omega t. In that case, the wave equation becomes k squared E naught is equal to minus mu sigma times minus j omega E naught minus omega squared mu epsilon E naught. So, all I have done is I have taken the second derivative with respect to z. So, I got a minus k squared and the minus sign got absorbed, and I got a, this is also plus, sorry, I got a minus omega squared from the time derivative, again the minus sign got absorbed, and here I get a jk, I mean j omega, because I have a single derivative of time in this equation. So, this now gives us our final equation. I can cancel the E naught out, I get k squared is equal to j omega mu sigma plus omega square mu epsilon. Let us go back to the case where we are in vacuum, then sigma is 0. Then I get k squared is equal to omega squared mu epsilon, or k is equal to plus or minus omega over square root of mu epsilon. The plus and the minus refer to the forward wave and the backward wave, because if the signs are the same, the wave is travelling in the minus z direction. If the signs are different, the wave is travelling in the positive z direction. So, that is what the plus and minus mean. So, this is nothing but, sorry, I think plus minus omega over c. Now, what do these k's and omegas represent? If I look at this form or this form, I am really looking at a wave which goes like cos of, I would like to say 2 pi times z over lambda minus C t, I should say t over capital T. Because I have a wave that looks like a sine or a cosine, I know that if I move in z by a distance of one wavelength, that is of 2 pi phase, I should get back the same point again. because cos is a periodic function. So, if I go this distance, which is usually called a wavelength, you have seen waves in sea water, waves in sound, it is the same wavelength concept. If you go a distance lambda, you should go a distance 2 pi in phase. So, this is what I expect from z, and if I go a time equal to 2 pi equal to time period t, then again I should go a phase of 2 pi. So, this is the form I expect, this is the form I have. So, I can immediately identify what k and omega are. K is equal to 2 pi over lambda and omega is equal to 2 pi over t. K is called the wave vector or the spatial frequency. Omega is the normal frequency, it is the angular frequency of the wave. So, k is like omega in the sense it has this 2 pi in it. You know that omega is 2 pi f, f is in hertz, omega is in radians per second, because 2 pi radians is 1 full cycle, which is 1 hertz. So, this is the relationship between omega and f, and k is related to 1 over lambda in the same way omega is related to 1 over t. 1 over t is a very important quantity, so we give it a name, frequency. 1 over lambda is usually not given a name. In fact, the only name that is given is to k itself, 2 pi over lambda. So, we have this expression relating the spatial frequency k, in other words 1 over lambda squared, to the temporal frequency, namely omega squared. And when sigma is 0, we get what we expect, we get a wave. But when sigma is not 0, we get something very different. This j is actually going to give me a complex answer for k for given real frequency. You can see that if I look at this expression and I write it in terms of real omega and imaginary omega, or real and imaginary, I will not say real omega and imaginary omega. Omega squared mu epsilon is along the real axis, j omega mu sigma is in the imaginary axis. So, when I add them up, I am going to get a complex quantity that is not pointing along real or imaginary axis, but in some general direction. And I want to take the square root of that. So, when I take the square root of that, this angle gets bisected and the magnitude I take the square root, that is my k. So, in general k is quite complicated. However, there is a very simple special case, which is also the most important simple special case. And that case is the case where I can ignore omega squared mu epsilon in favor of j omega mu sigma. Copper is an excellent conductor. So, when you go inside copper, almost all the time this term dominates. Since this term dominates, I have a situation that looks like this. This is the real axis, this is the imaginary axis, and I have j omega mu sigma. The square root must bisect this angle, and it has a value that is the square root of this value. this angle is nothing but 45 degrees. If I had to write what that unit vector was, it would be 1 plus j over square root of 2. That is a unit complex number with the same phase, 45 degree phase, as this vector. So, that is what I can write down now. So, my k, which is plus minus the square root of j omega mu sigma, is actually equal to plus or minus 1 plus j over square root of 2 times square root of omega mu sigma. Given that, let us just write down what the form of the wave is. I will complete the rest of it later. This is the wave. So, I have got e to the j times this k plus or minus 1 plus j over root 2 times square root of omega mu sigma minus omega t. Now, you can see there is a j here and there is a j here, and j squared is minus 1. So, this has the following dependence: e to the minus plus square root of pi f mu sigma times z times e to the j times plus or minus pi f mu sigma z minus omega t. So, there is a piece that has a spatial frequency and temporal frequency, and there is a piece that decays with z. I will complete this derivation next time and then talk about what it takes, what it is saying about making an antenna, making a receiver that can actually make use of the waves that arrive at the circuit. In a certain sense, that is what life does. You have light electromagnetic radiation coming on plants, and the plants cleverly take that radiation and make use of it.